Okay, so we've gotten to the Cyberdyne. Um, I like the Cyberdyne a lot. Um, I think I started this right as COVID was starting. I started the design for it, and it arose because I had a really important problem. Um, if you, this bike was being worked on. This is the Supermarine Spitfire, and it's a clunker, and it's got an 850 front center, which is about standard for mountain bike for average rider in my world, 5'10", 850. That's about what it works out to be. And because it's a fully rigid front, even with a design provision for a 3-inch front tire, the tiny head tube is very low. Well, because everything's moving down at an arc, I mean, along that arc, sorry, along that angle, I should say. Um, Unlike, say, a previous bike that had it, like the Warbird had a same front center, but a 180 fork. So the top of the head tube was way up here. Because this head tube's moving the same front wheel position, that's why we use front center, not stack and reach, because we want we want to make changes to this area, but not change where the wheel is, because we know where we want our wheel. So we want to move the head tube down. So while the bike will ride identically from a front wheel perspective, what other people might refer to as the reach of the frame will be much, much longer. And that's why we can't use that when we talk about bike design, because reach changes without the actual frame changing, you know? Um, so this bike was quite long compared to what I had previously done. And let me get back to that image. Where is it? In making the bike. Okay, well, oh, sorry. It's on the Cyberdyne. So here's my shop at work. And I have that bike on the Anvil Journeyman that I had at the time. But if you notice, what is it? It's setting up the bottom head tube puck location at 617 millimeters. I am effectively all the way at the end of what the fixture can do. In fact, I don't think this was even clamped down. Okay, so I had a real problem. My bike designs were exceeding the tooling that I had, and I needed a new frame fixture that would do the bikes that, from a traditional sense, are quite long. In the real world, they're actually just right. But the thing is, this fixture was never designed for anything close to this. So basically, I was kind of done with what I could do with this fixture, and I needed to solve that problem. Um, and I started thinking about it, and this is the blog post where I start talking about it. And lucky for me, right around then, we bought a Reiner cart at work. And this helped with some fixturing in the shop, and started changing the way I was thinking about fixturing. And it certainly that the whole way of using the 16 millimeter slash 5/8 welding breadboard has had a huge effect on my tooling. Previously, I was building around optical breadboard. Um, Now, the concepts are the same, but they are a bit different. Optical breadboard, actually, I've got some right here. Wait, let's grab a piece. Here, here's a little piece of optical breadboard. Okay, so what makes this different is this is aluminum. It's made for lasers and optical setups and microscope work in science apparatus. and it's got a 1 by 1 raster of quarter 20 thread holes. In metric land, it's 25 millimeter by 25 millimeter, which is very close but not the same, and 6 millimeter by 1 threaded holes. So in a science perspective, we kind of have to know what ecosystem we're in. At my work, it's mostly 1 inch by 1 inch. In other areas, you might be in a metric environment. Certainly, anybody in Europe is probably going to be in a metric environment there. And that set up the question. It's like, well, what kind of welding breadboard should be gotten, or if I was thinking about doing this again. And I decided that because I live in America, I work in America, and a lot of our stuff and support and everything like that, especially through Build Pro, which is uh, they've been kind of developing a lot as I've been developing this, and they have much more product than they had then. And they've been getting a lot better, which is really cool. But I think they have their boards made by Siegmund in Germany, um, and then they do their own distribution. So there's Siegmund in Europe, there's Build Pro in America. They're not the same in terms of like the hole diameters are a few thousandths different. I think the Siegmund's is a little bigger than Build Pro. Build Pro is specified as 5/8, but 16 millimeter tooling will work on it just fine. Siegmund, same thing, just the Imperial stuff gets quite loose on those breadboards. And this is a flat breadboard, which I don't think it's good in some ways, but not in others. I think for a good price you can get a decent enough breadboard, but I wouldn't mount it on the Rhino cart if I had a choice. The mounting of it is poor and leads to some distortion. Um, so I was like, okay, this is, and also it's made of 16 millimeters thick steel, which is quite rigid. I mean, this is 1/2 inch aluminum. It's pretty darn rigid, but 16 millimeter steel is pretty amazing in terms of how strong it is compared to what we might make out of aluminum. Um, but I had a quandary. I was like, well, I don't want to build something that only works on weld breadboard because I'm surrounded by optical breadboard. And optical breadboard, I mean, salvage on those is like, you can get those pretty cheap and easy, and you can get a 5 foot by 10 foot, 1 foot thick optical breadboard. It's honeycomb on the inside. It's not solid aluminum, but you can get stuff in optical breadboard that's fairly convenient. So I didn't want to like screw myself when I made this design. So I figured out that if I made these little nuts, these are a design of mine, I could effectively turn this breadboard into an optical breadboard. So I could design a tool. If it worked on an optical breadboard, it would work on this tool as well. So that was pretty cool. Now, over time, it's proven to be false or not good thinking. Now, I couldn't have known that at the time, but the thing is that I should not have worried about optical breadboard uh, as a consideration for mounting this. And that led to certain design problems that we'll see. Um, but it was my thinking at the time, and it seemed rational and everything like that. Um, of course, we do some math. We figured out I figured out some ranges, basically taking various bike designs that I'd done recently, and I figured out how much angle I needed and how much range in this way or whatever. And I figured out this cool system with these tool steel rails that would bolt up, and then I can bolt down to the table on a lateral position. Now, at first, because of course I have a lot of respect for what Jeff did over at Sputnik, I was really thinking about doing something like what Jeff does here with the XY adjustment of the front for the head tube. But I had a problem at the rear. And I was like, oh, I can't use that system. I need to like, I want to have a fixture that's intended from the start to be an offset seat tube, not something that was hacked to be an offset seat tube. Um, and because I was using a breadboard table, I had a lot of room to work. And I kept thinking about it and thinking about it. And I came up with this solution that would work for my seat tube. And thinking about it more, because you got to remember those early COVID things. I had a good month sitting on the couch, just thinking about ways of solving these problems. And it occurred to me that the solution I came up for the seat tube actually could work for the head tube also. And so that's what led to the Cyberdyne kind of rail slot system thing here. And you can see there that I do it for the head tube. And we're bolting down and we construct these rails. Now, I remember I'm not trying to defend every decision that I made here uh, against the test of time. The test of time has proven that I did make some mistakes with this fixture, and that's why we're talking about all this now. But I'm trying to put you in my head at the time, not knowing and having never seen a fixture like this before. So what you see here is that if I know the angle of this seat tube and I know the y of this rail, I can place this pivot of that seat tube anywhere along here that sets it up correctly. And it's just a little math, it's like here's the equations over here for this fixture, and we see head tube pivot X from BB, seat tube pivot X from BB. Basically 56.9 for, this is for the, again, the M2F2, is where the pivot is. If the rail is in that location, the pivot's going to be there. Where will that be? And of course, I can move the rail up to here and that dimension will change, but it'll then set that up at the same place. So we go in here and we look at our, oh no, where's our, I don't have the decals. Oh man, oh wait, maybe I have to view the decals. Here we go. Decals, come on. Yes, cool. Awesome. It's nice when models don't blow up, eh? Okay, so we have some decals on this because that's how we did our laser marking. Okay, so you can see there that this is a 50 millimeter shift from there, and it points right to where we need to be for that setting. So we're confirmed in the model as well as the math and all that stuff. Um, that's pretty cool. So figuring that out, so that it's like, okay, we're building an axis for the seat tube, but the shift is, it doesn't have to be coincident to the center of the seat tube. Well, that's great. And we find out, well, we can do exactly the same thing on the front. Notice the front, we've changed the height of the rail just for our convenience. And there's just another measure here where we set it on that tube. And if you look here, it's let's see, head to bottom from pivot is 15.24, which actually there's a new mark that needs to be on this, that this is the end, because I had a problem where I screwed up and read the wrong end. Anyway, so there's the measure there for that location, but otherwise it's just like the seat tube in terms of placing an axis. So we're placing an axis on a Cartesian raster, and then just on the head tube, we can travel up and down on that axis from wherever that pivot point is and locate the bottom of the head tube. So it's fairly efficient on that front. Now in the rear, we just do an XY, fairly simple type system here. And the angular stuff here, let's look at it. So I've got this marked in, what is this, quarter degree increments on my gradations at the top side here. This is wholes and halves. This is quarters down here. Um, but really, when we're setting this fixture, we're not really reading it. That's just a bullshit check. Because what we have, if you read this, we have a 270 millimeter cosine bar. Now, if anybody knows their machining type stuff, if you have 2 points there, let's say that point and that point, we know exactly how far apart they are. We can very accurately calculate the angle. And this is not the tool, it has round things and everything like that, but we're doing this off the cuff here, right? So if we know here and here the tangent touch points, it'll be a round circle otherwise, or a surface with rounds. So we know that angle. Well, I'm taking advantage of that, and while typically they're referred to as sine bars, because of the orientation here, it ends up being, because it's the complement, a cosine bar. And I have a pin here and a face here. And so what we do is we're linearizing an angular measure. So if I measure from the tangent point here to the face of this here, I can set it up by making a cosine block because it's 26 millimeters offset from the center line, adding both the pin radius and half of the beam, cosine of the angle times 270, we get a measure over here that will very, very accurately produce an angle. So we're actually getting angular, the trick when you're working on a flat surface is how do you measure angles? And you look at a lot of frame pictures that are developed out there, they're vertically oriented because, well, that's the only way they can figure out how to measure the angle. Um, or, to take a conformation check outside of the fixture, needing a vertical alignment because, back in the day it would be a plumb bob on an angle so that you could measure an angle, and then later a digital whatever it is, whatever the word is. I'm too old. Excuse me. Anyway, because we're laying flat, we can't use a tool like that. And we had to come up with a better way. And this nice big cosine bar, we actually end up with a superior way, which is really cool. Um, let's take another look at some stuff here that's kind of cool about this fixture. I'm actually going to hide this plate because it it actually takes some wear and tear on my RAM and processing to have that up. Surprisingly, that's what's killing a lot of the performance here. So let me hide that, and we can actually look at the underside here too. Come on. I have a very cheap laptop, so it's taking some time here. There we go. Boom. So let's take a look at the underside here. One of the nice things about the Cyberdyne also is underneath this pin for the angle clamp is a laser cut or a water jet cut. I can't remember which it was. Plate of stainless steel, similar to also these, because I didn't want grooves to be forming in the fixture, because that's pretty bad. And then we have pins. These ones have the O-rings drawn in them, and I need to get to that on the Cyberdyne too. So that just helps them stay in position under the table. And while I didn't have the pins I made with a hex, these ones are drawn with a hex. But you can see how simple that works. And we have just over 2 inches of slot length here. I can't remember right off the bat how much slot, but essentially it gives you enough range so that you're into the next slot or next pin location on the table to make any position possible while still having a nice rigid, I think these are 24 millimeter thick boards. Um, and then we come in here with countersinks. These pins are actually, these are countersunk screws. Let's hide this or transparent it. This is a countersunk. One thing nice about countersinking, we have a thing in tool making that we don't want to ever locate using a thread. That's tends to be bad form. You'll use pins and things like that to locate parts or faces, datums of some sort. But here I'm kind of cheating the system, and this is when it gets into like, you need to know the rules before you can break them. Well, I know I need to locate with a pin, but I can't use a thread, but then it gets cumbersome, and then it's a lot of parts and becomes a real problem. Well, if I use a countersink, and if you've ever spun a countersunk screw in a lathe, you see how wildly off they actually are. Like I would not just out of a box use a countersunk screw to locate something precisely. But if you just take it on your a collet lathe, hold it by the major, and clean up that face, now essentially you have, within reason, a tapered pin that's concentric to the axis of the threads. Well, kind of now we're using that as a tapered pin. It's pretty cool. And I think it works well enough, certainly for this type of fabrication, that you can end up with some positioning ease that way, okay? And of course, we don't need that up top because we're positioning linearly across a rail. Here, we're trying to lock it in place. And of course, these get some scales on them for that, for what they're going to need to be. I think in the earlier video I said about Jeff's fixture and how cool it was that you could not remove, you didn't have to change the fixture setting. Here, I kind of incorporate that. This is here we can hide this too, or change transparency. Ooh, I didn't clean that up. I need to make that prettier. Anyway, we have a quick release pin going through there, and the ball detent is sprung loaded against this taper on the other side and pulls everything together. And then there's some grooves cut in that slot to provide clearance for the ball. So you slide this pin, it doesn't come all the way out, it sits right in there. And then I have this second pin, and that's just there to clock the purge line so that the purge line down here is aligned to where it needs to be to go through that, because we have, if you're going to make a frame fixture, you should design it for purging, even if you're not building with titanium or doing internal purging. You can skip it when you're making it if it's an arduous process, but the process of designing it in means that if and when you do need it, you have room, you have a plan. That's the way to do it. And I try to do that with most of my designs, is design it the best I possibly can. If I need to take shortcuts for expediency, that's fine. I've got some screw jacks here. Because we're working off a surface, we can calculate exactly where this V is going to be. Let's see, does that get calculated in the sheet tube offset, sheet tube cosine? Oh, you can see I'm calculating the cosine spacers for each angle there too. I thought I had. Anyway, I do it somewhere else for this. So I calculate the height of that V for holding a round tube of that type. Oops. We need a new tower in here. Which tower is on there? Let's see, what configuration are we on? Axis tower. Oh, see, it's set up for a mountain bike. Oh, this is always good. There's a lot of different setups. In this model, I didn't fix that. I actually fixed it in real life, but I need to update the tower. There's a new tower design that I've been working on. Everything's updated. So you can see I'm 92.5 and 68 and 89 for those three, but there's a bunch more. TH47, we have 85.5 is what this one is. You want to have some room to adjust these things. Um, I built this stand. There's some problems with the design of this that have been improved on since, so we can talk more about that later. Um, it's largely, we have a 1 inch shaft going up through here. This is a steel ring support thing that gets clamped onto it, essentially unitizing those. So it's coming square off of that, and it's helping support that 1 inch tube. We've got some reducers here. And then it gets interesting. Let's hide this bottom bracket shell entirely. Okay, so one of the problems in designing a fixture is you need to get it off the fixture. Um, as discussed earlier, that was kind of a pesky thing with anvils, is how to get it off. And because I'm looking for a large degree of precision in my holding and everything like that, I want to reference that 1 inch diameter of this shaft as much as I can, and I want to support both sides of the bottom bracket because as we weld, everything distorts and rocks around, and so I'm trying to support both sides. And you'll see that a lot of fixture designs are only supporting one side of the bottom bracket, and I think that is a problem. But let's say this reducer here was fit to the bottom bracket tightly and to this shaft tightly. And then that bottom bracket shell distorts. Let's say it bends over the course of its run. That thing is going to be bound tight to that shaft and won't want to move. You know, there's a lot of force that gets generated from welding distortion. And so I had a problem. How do I fix that? And what I came up with, and there's also an improvement on this that get found at the end, I actually have that made in two pieces. This top piece here, where are our parts here? The taper lock section is actually fitting tight on the shaft. And then this fits onto the taper. And then when I go to release it, if it is bound, all I need is a little tap up here and move this cone a tiny amount. And then this cone, this reducer here will free up entirely. And that's proven to be very effective over the years and actually hasn't even required that much force to do. There's a newer version of this that actually has screws coming out of here. So it essentially turns into a gear puller, which is nice. But I'm showing the fixture as it sat when it was made type of thing. So that's pretty cool. We're grabbing that whole shaft, and it's a 1 inch shaft. It's not a 3/8 bolt, type of thing. We're really doing our homework on that one. We can hide this to see what's in there. So here I have a little gas pass there. In theory, this should be aligned, but it can hit anywhere in there. Nothing too complex, and then it travels up the tube and gets released out this hole, which is used for tightening it down on the table, so you can get some nice torque on that for a really firm thing. Firm cantilever force type of thing. It's a stanchion, but stanchion's just a cantilever, I guess. Um, Another cool thing about this design, especially when using the 16 millimeter steel, a lot of people make a fuss about needing an alignment table to build bikes and everything like that. And what's cool here, I mean, when you have one of these steel welding plates, they're strong. They're much stronger than bikes. And by having this nice solid pillar here in the frame fixture, I actually use this pillar for aligning the bikes too. So, whenever we're designing, we want, anytime we're making anything, we want to, if we're going to spend $1, we want to get $2.30 back, not 75 cents back. So if we're going to make something, let's make it once and have it do 3 jobs, that kind of thing. So here you're going to spend some money on a expensive welding table, and well, you should want to use that for frame fixturing, great, but also aligning frames, great. Also doing other welding projects that probably make you more money than making frames, um, and some other details that I can cover later. But this is a perfect example of like, oh great, I have a frame fixture and an alignment table in one. Not I need an alignment table because both these things take up a lot of room. I can't waste room like that. Um, what's another thing? Okay, this is another thing that got us into trouble. Let's open this part separately. I think this is an updated drawing for how it sits. Okay, there we go. So initially I was, whenever we're designing at a whole cloth, we think our expectations and understanding gets in the way. So I was so used to seeing Don's holder for uh, axles, dummy axles, that I just used that system because I have a bunch of dummy axles, and I did just the same way Don does. Like, here we go. Here's a modified for 80/20 rail, one of Don's things. See how it's nice and round. That is wrong. It's dead wrong. Don't do that. This gets into kinematic constraints, and I've I I hopefully made famous a discussion slash argument with Ronen about this, but he was right. He's usually right. Um, where it's ambiguous to locate off of that. We don't actually end up knowing. It's better to have two faces. We know exactly where the tangent points will meet. And actually, it's better to have just one side being the reference and not the other side, would be proper kinematic constraints, because then we've located the axis and then we've located the stop. Anything else is superfluous. So when we get here, and this is all very important when we're thinking about fixture design, and I've learned more over the years. Using this, you know, if any deviation exists for the diameters of the dummy axle and the slot, which there has to be for it to release, that dummy axle can twist, it can roll up and down in that area and everything like that. It can move in its position and won't be the same place every time we clamp it. And you can argue that it doesn't matter in this situation. It's like, well, it kind of does. Things add up, and we shouldn't take shorts, so to speak. We should do it right, and doing it right is proper kinematic constraints, and there's that. So I'm showing that off. That okay. And another problem I did with this design, while this elbow that holds that is beautiful, and it takes up very little space, it doesn't allow me easy height changes, and it also doesn't allow me calibration easily. You know, if we look at the the fixture top here, we need these faces to be orthogonal to this surface. That that's what we're referencing the whole bike on. As long as we're doing that, then at each point along the way, it should be good. Well, because there's variance in the whole tolerance stack up and everything like that, we generally will have to calibrate, even if all of our parts are made as good as we possibly can. Well, I didn't give myself enough room here for that. And that was a problem. And that's something we're fixing later on. So let's close that. Let's see if we can see anything more on this fixture that's cool. Because we want to understand what we've done, right? And we've done the Cyberdyne. Oh, I mean, more to jump off of where were we? Oh, let me see how that. Come on. This is sluggish. Okay. Oh, good. So update world, it does this when you get into really heavy shit. We lose all of our coloring. Um, I haven't figured out the best solution for this. Newer models are work more efficiently from a RAM perspective. This is some older modeling methodology. I've figured out some lighter weight ways of doing things. Um, and that's something you learn as you do solid modeling. Uh, oh, same thing over here with these tube support blocks. I had to modify those so that they're V blocks or they're V shaped. Oh, here, we'll just hide this tube. There. So those were round. That was definitely not cool right from the start. And now it's a V block type setup, which is properly kinematically constrained. Have some just rubber band tugs just like that. Just nice things to hold it down. These are nice thumb nuts. But what's cool about this fixture is if we put that plate back, where's the plate? Where's the plate? Okay, Rhino cart top. This will take a while to upload. Um, the big problem that I had to solve was I needed to be able to make longer bikes than I could otherwise. And this is probably a good example. This is a fairly low head tube bike, and while it has an 830 front center, unlike the 850, it's going to push most frame fixtures right up to their very limits. And here I have the width of a table where I can, if I use the full size welding table, I can make a bike as long as that table. If I have a 10-foot welding table, I can easily do it. If you make tall bikes, you can do that. Essentially, because of the way the fixture is designed, where you have the seat tube holder and the head tube holder and the axle holder, everything's separate. That means I can get a 510, if I did build tall bikes, I can make the finest tall bikes in the world because I can very accurately place them on a surface. Or I can work in a sub, I can just drop the rear and focus just on the front and extend this all the way out here. Someone very tall is probably going to end up in like the 900 millimeter front center area. We got to move this all the way out there. And so it's extendable. It's not dependent on the fixture and all that. It's dependent on the table or the way we use the table, or we can gang tables up. If you look at aircraft construction or higher end fabrication, you can gang these tables up with some alignment methods so that you can use 3 tables if you need to. So that's pretty cool. And we're not painting ourselves in a corner. Also, with this, oh, we don't have the torsion box. You can use MDF also for this. Just make an MDF torsion box. We'll talk more about that in Skynet. Um, and what else more is there that's really, really cool? Everything's purged. I have a multi-step cone and anyway, there you go. Oh, you can do fat widths. Uh, both ends are clearance for fat tires or anything like that. You can have, let's see, I have supports for it as well. They're probably not all set up. Okay, this is starting to run long, huh? Oh, supports. There we go. So, here we go. Let's put some supports up. So I've got my wheel tool in here. That's a whole different topic. But because we're working off this surface, oh gosh, there's the elephant in the room I haven't even mentioned. Um, so I primarily make hardtails. That's what generally works around where I'm at. But a lot of people want to make full suspension bikes. Um, Anybody that's done any research in kinematics and how those systems function know that some designs are very intolerant of the positioning of the pivots. Well, what's cool about this is because we have a raster here that's XY located in every way, these are messy, I could make a fixture that pins out on these locations and very precisely set up a pivot for or a shock mount or anything, and I'll know exactly where it is from a in a Cartesian sense. That's something that the beam style fixtures just can't do, or some of the other plate style fixtures don't give you what you need to do that. And here, if you're working with pivots or very specific mounting, you have that at your disposal, and it's very simple tooling to make. Here in the back, let's get rid of our wheel tool because we're not talking about the wheel tool. I have these towers that go in here, and they just clamp on the table, and I can set up a centered position of the rear anywhere I want, whatever length I want, or anything like that. So that's pretty cool. If I'm having stuff CNC machined, I just throw in some breadboard mounting there because that's fairly efficient. Okay, there we go. Come on, there. So excuse the messy. And we just clamp down right in position, and we can spread our seat stays right to where we want. We know what the center point is. There's a pin on this fixture for that, and that's from the table surface. Pretty easy. So we start making our rear end construction a lot easier, and if we were doing a production type thing, we could have a dedicated spacer all set up and ready to go. So you just rubber band. Um, okay. I think that's it for Cyberdyne. I've been using this for a while. I will say it's got problems. That pinout type slot thing is a real pain in the butt. Also on here, it's just a drag to be undoing and doing bolts all the time when you're setting up or adjusting or loading in and out. I don't like that. I love the rigidity. It is a rigid tool, and that's really nice. I like that I can use it to bend things around. I get a lot of measurement points. I can build anything I want onto it. So it has worked out in that respect. Okay, so that's Cyberdyne. We're going to talk about the Skynet next, I believe. So let's stop this video.